just before we look at example 9 here for finding the area in between a curve. Notice it's often preferable to use only the area in the first quadrant when a curve is symmetrical in the other quadrants. Thus, in the above example, instead of using a half of this, we could use 2 times this. That's exactly what I said just at the end of the previous video. I should have added it in there at the end, but it's just in there below. Example 9, and find the area bounded by the curve r equals k theta and the lines theta equals pi over 2 and theta equals pi. This is part of the Archimedean spiral, again, if you remember from one of the previous examples. So a quick sketch of this. Remember, we're in between pi over 2 and pi, so it's in between 90 and 180, which is a slightly weird part to be trying to do. So a very quick sketch of this. We'd then be going from there round to there. So that's the area then that we're looking for. Okay, and that's obviously your formula then. That's going to be k pi. And then that's your k and pi over 2. So the curve r equals k theta is shown for here. So that's this wee bit of it here. And then the area that we require is going to be a, again just using our formula, is a half in between pi and pi over 2 of k squared theta squared theta. Again, I hope you see where that's come from, because your formula is r squared, so we're just squaring this wee bit here, and we end up then with that. I'd probably take the k squared out here before we actually do the integration, so we're going to go k squared over 2 upon theta, add 1 to the power, divide by the new power in between pi and pi over 2. That gives us k squared over 2 upon pi cubed over 3 minus pi cubed over 24. And you can either do your sums or take my word for it, but that's going to give us 7 k squared pi cubed all over 48. So that's the area then of this particular shape here.